Application of linearly independent vectors. Prove that the opposite sides of a parallelogram are congruent. Well, we all know about it, correct? Now we'll use this property of linearly independent vectors to prove it. Let us see how to do it. So let's first draw a parallelogram. Let's say that's a parallelogram. So what we are given in a parallelogram is that the opposite sides are always parallel. That is what a parallelogram is. So opposite sides are parallel. Now what we need to prove is that they are equal also. So that is what we need to prove. Now to prove it, we are going to use what we have learned about linearly independent vectors. So let's kind of review that. So what is linearly independent vectors? So linearly. So what we have learned about them is, first we know that vectors are linearly independent if they are not parallel. So let us say there are two vectors u and v. So we say they are linearly independent. That means they are not parallel. Correct? If they are parallel, then they are linearly dependent. Another thing which we learned about them is that if we have a linear combination, let us say if I had AU plus BV equals to 0, and if the vectors are linearly independent, in that case both A and B should be equal to 0. So these are the properties which we have learned about linearly independent vectors, and actually we are going to use these properties to prove that opposite sides of a parallelogram are indeed congruent. Correct? So that is what we are going to do. Let's see how. So let us say that we have these vectors as parallelogram side vectors as u and v. So let's say this is my vector u and that is my vector v. Now if I am saying that opposite sides are not parallel, if I am saying that the opposite sides are not congruent, that means they are scalar multiples since they are parallel, correct? So this side could be a times u and the other side could be b times v, correct? If they are not congruent, then, but they are parallel, so they are scalar multiple at least, correct? Where a and b could be any number. If they are congruent, in that case a and b should be 1, right? So if we prove that a and b are 1, that means that the opposite sides are congruent, correct? So what we are assuming here is that the opposite sides are scalar multiple, of course, since they are parallel. So let them be BV and AU, right? So that is how the opposite sides are. Now let us say what is the diagonal. Let me join the diagonal and label our parallelograms. Let me write A, B, C and D. Now in that case, what is AC equals to? We have AC is equal to U plus V, right? How about AC from the other side? AC from the other side will be equal to BV plus AU. Now both should be same, right? So what we can do is that we can write this as UV, U plus V rather, equals to BV plus AU, right? Bringing them together, what do we get? We get U plus, rather minus, we are bringing it, this one first I'm writing now, U, rearranging, so we have plus V minus BV. So I'm rearranging them also, writing both the vectors together, equals to 0. Now if I take u common, then what I get is 1 minus a times u plus, if I take v common here, 1 minus b, v equals to 0, correct? Now, since we know that u and v are not parallel vectors, correct? So they are not linearly dependent. If they are not linearly dependent, in that case, this equation, let's correlate these two equations now. So that really means that the coefficients of u and v should actually be 0, right? So that gives us that 1 minus a should be equal to 0 and 1 minus b should also be equal to 0. Is that okay? Both, right? And therefore, solving, we get a equals to 1 and b equals to 1. So as you can see, from our assumption, we said AD is equals to BV, right? And we have DC equals to A times U, correct? Now since A equals to 1 and B equals to 1, we have AD equals to B is 1, right? So AD is equals to V, and DC is also equals to U. Do you see that? So we have proved that the opposite sides are exactly same. Do you see? So that is how we prove that AB is equals to DC and BC equals to AD. Do you see that? So that is how we can prove it, using the properties of linearly independent vectors. I hope the concept is clear. So what we do is we start with a parallelogram, assume that the opposite sides are not parallel, so they will at least be scalar multiples since they are parallel, right? So AB is taken as vector u, DC should be A times u, scalar multiple. BC is V, so AD should be some scalar multiple of V. Now if you see the diagonal, then diagonal is same for both the sides. We could write AC in terms of u plus v, and we can also write this as BV plus AU. Now since these two are equal, equating them, we get a linear combination. Now this linear combination is 0 only when the coefficients are 0. If the vectors are not linearly dependent, so they are independent vectors. Now equating them to 0, we say that, well, A is indeed 1 and B is also 1, no other number but just 1. So that shows that the opposite sides are indeed equal. Do you see that? So that's how you can prove that the opposite sides of a parallelogram are congruent. Thank you.